of the reference tables again, and we're going to need a piece of scrap or magic paper to do this. We're going to use the data that we calculated in part 3 of our activity where we were calculating lag time. So we're going to use these time differences of 2 minutes and 35 seconds, 8 minutes and 52 seconds, and 9 minutes and 30 seconds. What we're going to be asked to do at this point is to use these lag times or these time differences to calculate the distance to an earthquake. Geologists need 3 different station recordings to triangulate the location of an earthquake epicenter. We are going to be using these time differences in a method that is called the slide method, or sometimes it's called the wedgie method, to figure out how far from the epicenter that recording station is. So what we need first is our magic paper and our time difference. And we said the first one was 2 minutes and 35 seconds. So we're going to get as close to 2 minutes and 35 seconds on our scale as we can. This is 2 minutes here, 2 minutes and 20 seconds, 2 minutes and 40 seconds. Now we got to take our magic paper and measure the distance that 2 minutes and 35 seconds takes up on our paper. So I'm going to make sure the edge of my magic paper is level with my 0, and then I'm going to mark off very close to 2 minutes and 40 seconds. So this distance here represents that time difference. Now remember, that is the difference between the P wave arrival and the S wave arrival. So we need this amount of time in between our 2 waves. So what we're going to do is we are going to take our magic paper and we're going to lay the lower corner against the P wave. And then we're going to slide our paper over to the right until we get that 2 minute and 35 second difference. Now you'll notice I'm being very intentional about keeping my paper vertical. You can use these lines, these vertical lines, to make sure you're doing that. But I want the edge of my paper to touch the P wave and my pen mark to touch the S wave. Once I have that, I am going to read the distance on the x-axis, and I get 1,400 kilometers. So I'm going to write that down. When the P wave arrives 2 minutes and 35 seconds earlier than the S wave, the distance to the epicenter is 1,400 kilometers. Now let's do our 8 minute and 52 second arrival time. We're going to do the same thing. We're going to lay our magic paper along the x-axis. And here's 8 minutes and here's 9 minutes. Our pen mark is going to be very close to the 9 minute mark because this is 8 minutes and 40 seconds here. 8 minutes and 52 seconds is extremely close to 9 minutes. Again, I'm going to be very careful to make sure my paper remains completely vertical, but I'm going to move the corner onto my P wave. And obviously this distance is a lot bigger, so I'm going to have to move my paper over much further to the right. I am going to get a match right about here. Yeah, that works. And then I'm going to read my x-axis much further this time, 7,600 kilometers. So an 8 minute and 52 second difference gives us a distance of 7,600 kilometers. Now we can do that with any time difference. Our 9 minute and 30 seconds might be about the upper limit of what our reference table can handle. So 9 minutes and 30 seconds. I'm going to move it over. And it looks like I am going to get a distance of, make sure I keep my paper completely vertical, 8,200 kilometers. Now we're noticing a pattern here. As the time difference gets bigger, the earthquake is further and further away from our recording station. So what we first have to make sure we do is calculate the correct time difference first, and then we can use that time difference to calculate the distance from each recording station.